Good afternoon. Welcome to a session. So my name is Olivier Tardieu. I'm a principal research scientist and manager at IBM Research. And today I'm joined by my IBM Research colleague, Dave Grove, and Claudia Misale. And we're going to talk about how to build, operate, and use GPU clusters for AI. Right? So by now, we've all heard about AI and Gen AI. We are all probably excited about it, but we're also sometimes a little bit anxious about it for lots of reasons. And as an organization, maybe the first reason to be anxious about AI is to actually procure GPU to do AI, right? It's both time-consuming, expensive, slow, whether we rent them from a cloud provider, whether we buy them, whether we lease them, whether we want a dozen of them or 1,000 GPUs, it's a big problem. But someday we'll get them. And then the second panic arises, right? It's how can we take these GPUs, this pool of resources, and somehow share it across all the teams, all the users we have in our organization, all the projects that need access to these resources, so that we can manage them and we can maximize utilization and we can maximize the return on investments. So this is something we've been working on IBM Research on our own cluster for several years now, and we've essentially built a point of view, incrementally refined methodology, a setup, and we're going to try to share this with you today with the hope that it can help you with your own AI journey, and also that you will tell us everything we could do better. So let's get started. So what we're going to show you today is entirely open source. Everything is available online, including this tutorial. So if you go to this QR code and this URL, you'll find all the commands, all the scripts, all the YAMLs that we're going to use today, and you can conceivably follow along or replay that at home, right? So because we're going to talk about GPUs, that I don't typically travel with 2,000 GPUs in my backpack. This is all going to be recorded demos, but on a real GPU cluster. So I'm going to start by a brief background on AI/ML workload, on the kind of hardware we target, on what exactly are the key components and maybe the key goals of the platform we've been developing at IBM Research, and then we'll get into the deep dive of the tutorial. How do we set up a cluster? How do we onboard users? How do we do things like monitoring, fault tolerance, and also what kind of workload templates we give our new users to get them started on these kind of clusters. So let's start with AI workloads. Again, it's probably not worth spending too much time on this because you probably heard a lot about that before. There's essentially an entire zoo of workload, the collections of things we want to do, all the way from having the idea of a Gen AI application to actually running this application in production, right? And what we're interested in discussing today is this piece of the pipeline. Again, it's more than a pipeline, all kinds of feedback loops, bypass, and so on, that are dependent on accelerators, such as GPUs, and that are typically batch workloads, right? It's not about running the application at the end of the day. You have lots of other talks at KubeCon about running large language model, running agentic frameworks, and so on. We're not going really to get into that today because also in sense it's the scope, really there's a lot of optimization and special things you want to do for that. What we're going to focus on is everything that happens before that, right? Everything starting from things like data preparation, even, like when we do hate and profanity filtering, for instance, on our data, before we train models, we actually use already machine learning models to do that, so we need GPUs, we need a lot of resources, training models, fine-tuning models, running batch inference, for instance, for validation of other kinds of workloads. This is the scope of what we're trying to run on these clusters, right? Other than that, what's also interesting about AI/ML workloads is they are very intensive, so they can use lots and lots of GPUs at once and run for a very long time. And finally, they depend a lot on AI/ML frameworks, like, for instance, PyTorch, and having good support for that out of the box is really critical for enabling users to do anything with these clusters. So from these requirements, you can see on the other side of the slide a number from these properties, you can see a number of requirements arising, such as how we're going to queue workloads, how we're going to prioritize them, manage quotas between teams, how do we deal with large workloads, in particular with this kind of Hardware, I think everybody in the industry has been reporting that GPU nodes are more complex than traditional nodes, therefore they have more, maybe creative ways to fail. We have longer running workloads. How do we do fault detection and all of these things? So in terms of clusters, what we typically run at IBM Research is large clusters with NVIDIA GPUs like A100 or H100. So here you have two kind of node generations we've used or we're using that we've published detailed specs for. So on the left, the more like the first generation A100 nodes. On the right, you have something more recent, which is an H100 node. And the key characteristics of these nodes is they have a high density of GPUs, right? So they have 8 GPUs in both of these pictures. And then lots of compute, CPUs, memory, local storage, high-performance network, and so on. So that's the kind of things we want to run with. So, and finally, I want to briefly tell you a little bit about what we're going to see in the rest of the tutorial. What is the kind of platform we're trying to build on? And because I think we're all engineers here, rather than starting with abstract goals, let's be very concrete and start by looking a little bit at the components, right? This is the kind of things we put together in this platform, and we're going to review one step at a time, right? Of course, in the middle, you have Kubernetes. We start there. And it's not just because it's KubeCon. I think yesterday in Cloud AI Day, we had somebody bold enough to ask the question, why Kubernetes? And I think for us, the answer is really simple. It's because of the vitality of the community and the CNCF landscape, right? How many projects, how many things we can leverage from the community contribute to the rate of innovation that makes, if any, is second to none, right? Any other choice would require a lot more work to get to a platform. And so that means not only we have Kubernetes, we have projects in the Kubernetes community like Kueue, but if you take something like PyTorch, which has nothing to do with Kubernetes in the first place, we do get things like Kubeflow Trainer that the Kubeflow community has developed so that we can easily run PyTorch on Kubernetes. We also have on the right-hand side some of the new projects we as IBM Research have introduced, where we found that maybe the community landscape was still lacking some critical capabilities for what we're trying to do, and we'll get to that in a few minutes. So what is the goal of our stack, again, at the high level? It's to manage workloads and resources on Kubernetes cluster for AI. It has to be open source. The components, the upstream components, the new components, the combination, the composition of these components, everything. I'll repeat that multiple times throughout the talk. It has to integrate key AI/ML framework. It is about multi-users, right? Within an organization, how to manage having many users without conflict popping up every day between them. It is about productive utilization, because at the end of the day, we're paying a lot of money for these GPUs. They have to be running all the time, doing something useful all the time. And we insist on fault trends, and of course, to the side, you have monitoring, observability, and so on, that always are a critical piece of such an infrastructure. So before I move on as well, again, I said open source. So everything we're doing today is open source. Everything is meant to run on vanilla Kubernetes. But obviously, IBM, Red Hat, we work together, also provided supported versions of this kind of technology. So in this space, what we're doing is working on OpenShift AI. So if you want a supported solution that essentially overlaps what we're describing today, you'll find this in OpenShift AI. OpenShift AI does more things than what we're discussing today. For instance, looking at how to run applications at the end of the day. MLmatch does more things because it's a research platform, and we're trying to figure out the next thing and the next thing and the next thing we want to add to OpenShift AI. But again, for the rest of the talk, you can forget about that. I should also say again, to be clear, that we are going to run our demo on an OpenShift cluster, because this is the Kubernetes flavor we prefer in IBM, but there's nothing that is really dependent on that. So let's start from the top. Here's to give you a sense of the cluster we're going to run this tutorial on. It's a small version of what we run in practice. It is a cluster with 6 nodes. 3 of them are control plane nodes, and 3 of them are worker nodes, and the The critical bit here is that this piece of information is that these worker nodes have a number of NVIDIA GPUs, 3 times 8 GPU, 24 GPUs, NVLink, and what I had pictured a little bit earlier. This cluster is kind of in between the 2 generations I was showing you before. So before we start, right now we have a base cluster, nothing on it. We need 2 prerequisites, essentially. We need to fulfill 2 prerequisites because before we move on to actually installing ML batch on this cluster. The first one is we have to teach the cluster how to manage GPUs. As you probably know, Kubernetes out of the box understands CPU, understands memory, ephemeral storage, has a certain number of resources built into the scheduler, but not GPUs. In order to do GPUs, NVIDIA GPU in this case, you need to install NVIDIA GPU operator, was jointly developed by Red Hat and NVIDIA, and that will add an extended resource type to your cluster, nvidia.com/GPU, and that means now you can start having workloads with GPU. So we've done this beforehand. It's OpenShift, so we click on the boot button on the console, it gets deployed. But if you have a vanilla Kubernetes cluster, NVIDIA has a lot of documentation online how you can go and deploy a Helm chart on your cluster and have all these set up for you. So we're not going to review that. Second, we're doing AI. AI depends a lot on data, therefore storage. So we need some kind of storage solution for our cluster. So in practice, we want to have high-performance storage solutions. For instance, we use IBM Spectrum Scale. But for the purpose of this demo and what I'm including here is that we can, let's say, just assume that we have storage available through an NSF server on a local subnet, and then, just following adding an Helm repository and installing an Helm chart, we can make this available on a cluster as a storage class, and from that we can create persistent volume claims and access storage, and so on. So now we move on to the cluster setup itself, right? And there are 2 parts to it. First, when we set up a cluster, there's what we do once. What does the admin do when we create the cluster? And I normally never has to worry again about, right? And then there's a second step, which will be the team and user setup. How do we onboard teams? How do we create user? How do we give them the right permissions? So I'm going to review these 2 things. And to start with, the cluster setup is pretty straightforward. You can do this by cloning the repository where we have all of our supporting, again, tools or scripts and so on. We set up priority classes on our cluster. In practice, we've seen that having low, medium, and high priority AI workloads is enough for what we need. We deploy the key components. Some of them are scheduler plugins, some of them are operators. We're going to actually talk about each one of them in sequence in the next hour or so. And so I'm not going to describe them more here. As I said, we can deploy them through OpenShift AI or without. We configure Kueue, which is our queuing system. We'll talk about that. And we finally have to create a role. That is the role we're going to give users to give them permissions to run workloads, monitor workloads, debug workloads on this cluster. So that's the cluster setup. And that's pretty much it, right? Then we have the team setup. And again, that's pretty boilerplate, right? In our experience, it makes a lot of sense to associate a team and a namespace. So when we want a new team on a cluster, we create a new namespace. And then we have to only do 3 other things. We have to set up a queue for that team, which is where the jobs submitted by that team will be queued. We have to make this queue the default for that particular team, which is the local queue definition on the left. And finally, here we're creating user Alice in Team Blue. We have to give Alice this RBAC, this role that I was describing earlier, in the namespace Blue, so that now Alice is officially a member of Team Blue and can use the capabilities of the cluster in that team. But I forget, maybe we need to label the namespace so that we say ML batch is managing the namespace. And really, the only thing that is not entirely boilerplate on this slide is what I've highlighted on the right. It's defining how much quota we're giving to this team, right? So here we're saying, well, Team Blue should have nominally access to 8 GPU on that cluster. So I'm saying nominal here, and we'll get back to that. But essentially, Dave will go into great details into quotas. That doesn't mean that Team Blue is limited to 8 GPUs. If nobody else is running on the cluster, they could access the entire cluster, but that means they essentially have guaranteed access to 8 GPUs on the cluster. So I have a video going through that that you can also find on YouTube. I'm going to go through. So this is an 8-minute video on YouTube because I try to describe what's going on as I'm running this, but really fundamentally, this is just a minute to do this setup, and this is pretty boring. So I'm going to go quickly. Again, you have the tutorial scripts I've described. I gave a pointer to earlier, and what we do in this setup is we go and we copy-paste instructions from the left to the terminal on the right. So first, what I'm showing on the right is what I was showing before on the slide, that we have this cluster with 24 GPUs available. So if I, for instance, connect to one of the nodes, I can see that they're one of the worker nodes. I can see I have 8 GPUs available here. Second, I can check that the GPU operator is already installed on the cluster. So we can see the GPU operator is already installed, which means if I query the capacity of the node, of a worker node, I can see here that I have 8 GPUs available as the capacity of that particular node. And then I can set up my storage class, which I was, again, showing earlier. Again, it's as simple as copy-pasting the setup. So this particular case, again, we're doing something simple, a simple storage class. The way you would set up storage will depend quite a lot about the kind of storage solution you adopt for your cluster. Also, what's maybe oversimplified here, we have no authentication of any kind. We're just assuming the storage server is on the same local network, and that's where the security is happening, right? Nothing, no credentials, and so on. So real setup, we'll have a little bit more than there. And then we move on to the ML batch setup itself. And this is just running a long script that has all the components of ML batch I was describing earlier, or will describe later, actually, such as Kueue, Kueue, Kubeflow, and so on. That's all it takes to set up the cluster. The last thing I didn't mention in the slides is we're also going to reserve some capacity in the cluster as an admin queue for admin to do maintenance operation. And again, this is something we'll explain in details in 2 minutes. In that particular setup, I'm also reserving 8 GPUs for this admin queue. That's it for the cluster setup. Then you have the team setup. Here, for the purpose of the demo, we're going to actually set up 2 teams. Team Blue, I went too fast. We set up Team Blue with user Alice, as we've shown in the slide. We're also setting up Team Red with user Bob, which is, again, the exact same thing with the 2 names replaced. I think that's it for the video, so we can close this. That's it for the cluster setup. Before I pass on to Dave, I want to describe the very first components of this setup very briefly. Happy to answer questions maybe after the tutorial if you care about that particular piece. One of the components of our ML batch setup is to actually deploy and configure scheduler plugins for a number of reasons. Essentially, this is about trying to avoid fragmentation in the cluster. So that's the purpose of the node resource fit scheduler plugin. What it says is if I have, let's say, a workload that requires 1 GPU, I should try to fit it in a small hole in my cluster, right? If I have a node that has already 7 GPU utilized and 1 left, I'd better put it there than put it on a node that is entirely empty, because if later I want to run an 8 GPU job of my cluster, then I'm no longer going to be possible if I fragmented my cluster. So we use scheduler plugin to try to avoid fragmentation. We use scheduler plugin to do gang scheduling. The idea there is if you have a large distributed AI/ML workload that needs 256 pods to run at the same time, we want to make sure we can fit the 256 pods before we actually deploy any of those pods, because deploying 250 pods is completely useless for most AI workloads, so we use co-scheduling for that. Finally, we have an experimental plugin we've also developed at IBM Research to do topology-aware scheduling. This is something that is coming in the community as becoming important. Kueue is working on that. A number of people are working on that. The idea there is to If you have a distributed workload, we're trying to make sure we distribute it as few racks as possible to maximize the bandwidth, minimize the latency of communication between the different components. Okay. Dave, just take it away.
Good. All right, so thanks. So now what we're going to do is we're going to dive into some detail into some of the components in the stack, starting with how we do queuing and quota management. And for ML batch for queuing and quota management, why do we want quotas? So quotas, we want to set up these large shared clusters so we can make more efficient uses of resources. So we can have large clusters with a large number of GPUs on them. We can share them across a bunch of teams. And that lets us both share the resource pool so people can have a little bit more fungible resource pool. And we share the control plane, and we also share the maintenance, the admins it takes to run these things and set them up. It's easier to set up a small number of large clusters than a large number of small clusters. But native Kubernetes quotas by themselves are not enough. Right, so quotas, first of all, quotas are done on the level of pods. Quotas aren't aware of workloads. They aren't aware that you're actually running something that contains a lot of pods, and so the quota needs to be done on that sort of workload granularity, not the individual fine-grained resource. Secondly, quotas are fairly inflexible. So this picture on the right, I want to take my cluster and divide it between two teams. I can either divide it exclusively. A and B get pieces of it, and then there's no, if A isn't working and B is in another time zone and they're asleep, no one's using B's quota. Or I can overlap them, and I can have some reserved for A, some reserved for B, and some stuff in the middle that either one can use. But then there's sort of no fungible, no fair borrowing, no fungible quotas, and really no trade-offs that way. And so this quota management is one thing that the Kueue project really does a much better job of. So Kueue is a Kubernetes native system to manage queuing, quotas, and jobs. And in ML batch, Kueue is entirely in charge of, for users, figuring out when their jobs they submit should wait, when should they be admitted? So when do we actually go off and create the pods and resources to start running these things, when they get quota assigned to them, and when things should be preempted. So when something's already running, but something more important comes in, or something from another team comes in that needs the quota back, so should that job be suspended or so on. So Kueue has a number of features. For us, some of the key features are it has workload aware quotas, so the quotas are done on the level of the top level jobs, not on the individual pods. And Kueue knows how to admit that way. It has mechanisms for fair sharing, for queuing with priorities, for preempting jobs, and so on. And it's also externally extensible, so it allows people to customize what's going on. And has built-in support for popular job settings. And so what built-in support means is the way Kueue works is each of the controllers for those resource types has had a small extension made to it. It understands a suspension protocol. So when the resources are first created, they're suspended. And then when Kueue wants to admit them, it flips a bit on the spec saying, okay, your suspend bit is now false, you can go ahead and run. And all the controllers are extended to do that. So there's the project there, and actually Kueue has a booth over in the project pavilion, so come over there if you want to learn more about Kueue in a lot more detail than here. I'm going to talk a little bit more about how Kueue works in particular to give you a sense of it. So the key thing is Kueue's that green box in the middle. And what Kueue is going to do from a user perspective is interpose on the creation of resources. So the user wants to submit a job. They just you do the usual kubectl apply or create. The resource gets created. Then Kueue has webhooks that interpose on the creation and look at it, decide whether, based on the namespace and other characteristics of it, is that something that Kueue is supposed to be managing? If so, it suspends it. It modifies the spec before the thing gets created to set suspend to true. And that causes the controller to then look at it and say, oh, this is inactive. I'm not supposed to do anything with this yet for the resource. And so it sits there until Kueue decides that it's time for that thing to run. It has quota. And that sort of admission protocol can involve looking at external resource checks. That's the purple box over the far side. It can also interact with the cluster autoscaler to ask it, is there capacity yet? Oh, there isn't capacity. Can you create some capacity for me? Let me know when it's available. And finally, when all that happens, then Kueue can decide to admit it, at which point the suspend bit is changed from true to false, and the underlying controller, whether it's the job controller, the PyTorch, the training operator, whoever's actually really in charge of that resource, now sees, oh, the suspend bit is false, now I'm supposed to do my normal job. And everything just sort of continues as normally. The controller for that will go off and create the resources, it'll eventually create pods, the pods will be submitted to the Kubernetes scheduler, they'll be run, and so on. Right? So the key here is having that interposition mechanism in the middle where you can suspend something and cause it to wait for its turn. And one of the key abstractions in Kueue that we're going to be talking about is the notion of a cluster queue. So Olivier talked about this for a second, or a little bit already. So the cluster queue is what is assigned quota. So one of the things the cluster admin does for each one of our teams is he creates a cluster queue for them. And the YAML on the right gives you a sense for what that might look like. In particular, the resources, the quotas that's assigned to that team is shown on the cluster queue. And there's also some additional detail about what are the preemption policies and how do these cluster queues work together. In particular, Kueue lets you put cluster queues together into a cohort, and these cohorts, the cluster queues within a cohort, can then coordinate to borrow quota from each other. So if there's quota available in cluster queue A, and cluster queue B needs it, and they're in the same cohort, it can actually borrow that quota from it, and then the quota can be taken back when it's needed by the other cluster queue. So it's a way to sort of have a more flexible quota system where these things are grouped together. And we don't use it in ML batch, but more recent versions of Kueue actually support hierarchical quotas. You can hierarchical cohorts. So you can sort of put these things into a pyramid together of sharing and preemption, and get that all to work together. So your cluster queue structure could match your organizational structure, where you have teams that are associated with a particular division and a particular vice president, and they all have their quotas and they're assigned around. And so they can negotiate among themselves how they want their quota assigned and so on. And so that's the notion of a cluster queue. A second thing, one of the projects we built within IBM Research is this thing called App Wrapper, and this came out of our experience of running these more complex workloads. And App Wrappers really do two things for us. So one of the things they do is they allow us to group multiple resources that logically belong together into a single workload that we can then hand to Kueue to manage. So App Wrapper implements the Kueue suspension protocol, sort of our lifecycle diagram on the right there. So they start out suspended if Kueue is supposed to manage them. When Kueue admits them, we realize that. The controller then goes through an internal lifecycle, which we're going to talk about a little bit later, to actually create the resources. And if it gets preempted, it'll be suspended and take those resources back. So it lets us group resources together. So we can put any number, several compute resources together, anything that's defined using a pod spec template. That includes all the built-in kinds that come with Kueue, that Kueue has built-in integrations for, can be put inside an app wrapper, but also additional kinds that Kueue doesn't know about yet, but are defined in terms of pod spec templates. App Wrapper gives you an easy onboarding path to get those to run on Kueue. And it also lets us put auxiliary resources in there. So sometimes people's workloads require services and secrets and ingresses and other things associated with them. We would like those to be all sort of logically managed as a single unit, deployed on the cluster when the cluster is admitted, when the workload is admitted by Kueue, have all those things created, and when the workload is done, have them cleanly cleaned up so we don't have lingering services and ingresses kicking around because someone forgot them. The second thing that app wrappers do for us, which we're going to talk about in about 15 minutes, is they harden workloads. So app wrappers are a key part of our fault recovery process, and they allow us to monitor the workload health, have a way to configure our retry and failure policy, and make sure that all the resources are cleaned up and done like that. So we're going to have a demo of that later. What I'm going to do now is switch to this demo, which is talking a little bit about demonstrating some of the quota and preemption properties of the system. All right, so we're going to start off, for this particular demo, we're just going to be running sort of synthetic workloads, as they're all sort of variations of this YAML that's shown over here on the left. So these are just sleep jobs. They start up, they create 2 pods, they request some GPUs. The 4 kinds of jobs we're going to be running. The characteristics are shown in the table down here, and we're going to use these to illustrate some of the characteristics, some of the properties of Kueue, its queuing, its preemption, and how quota gets shared across teams. Up on the right, this thing over here is called QViz. This is a new visualization tool that's being developed as part of the Kueue project. And it gives us a way to sort of look at the state of the system. So in particular, what it's showing here is the cluster queues for Kueue. So these are the 2, we have 3 queues, the red team queue, the blue team queue, and the Slack cluster queue. So now we're going to go ahead and start. So Alice comes into work, and Alice is going to create a burst of short-running jobs. So each of these jobs is going to run for 30 seconds. They're each going to create 2 pods. Each of those wants 4 GPUs. So she's submitted 32 GPUs of work to a cluster that has 24 GPUs. And so some of them are going to have to queue up. My math isn't very good. 6 times 8. Well, she's done more than that. But so she's created 7 jobs. So 7 times 8 is 56. But only 3 of them are running. So she's got 3 jobs that have been admitted. They're using the 24 GPUs on the cluster. And the other ones are waiting because there isn't enough resources for them. So they're just queued up. The pods aren't even created yet. And you can notice here that Alice actually is using the whole cluster because the cluster's healthy, we don't need the slack capacity, and the red team hasn't shown up to work yet. So Alice, even though her nominal quota is 8, she can run 24 GPUs. And we can look in QViz, you can drill down into the local queues. So here's the view of the red team and the blue team local queue. This is their mechanism in their namespace for submitting stuff to that cluster queue. And we can see that she has those 3 workloads. And QViz lets you drill down into the workloads as well, so you can sort of drill down and see what each one of those workloads is doing, what its state is, and so on. All right, so now some of her short-running jobs have finished, and so some additional ones have been emitted. Now she only has 1 pending job. But unfortunately for Alice, Bob on the red team has just shown up to work. So she has some, oh, sorry, no, that's not what we're doing. All right, so now what we're going to do is we're going to have Alice, so we can talk about queuing and preemption, we're going to submit some long-running jobs. So now Alice has now submitted 4 jobs that each are going to run for 10 minutes. All right, and so as the short-running jobs finish off, the long-running jobs are going to start running. All right, so here we are. And if we look at the pods, we're going to look and see, first of all, we can see that I can't type. Oh, there we go. All right, so we can see the pods that Alice has in the namespace. Some are running, some are completed. So we can see a mix of the short-running jobs, which are mostly done, and then normal jobs, which are starting to go. And we can see that those are there. All right, so now I think it's time for, oh, right. So Alice has created a bunch of sort of normal priority jobs. And she's queued up and some of them are waiting, but then she realized she had something really important to do first. So Alice can use priorities to have one of her workloads jump in front of the queue. So she just created an important job, and that was created after all the other ones, but because its priority was higher, Kueue has already gone in and suspended one of her normal priority jobs to make room for her important job. So Alice and her team are able to manage to use priorities to organize their own work and to make sure that things they really want to do get done first. And we can see on the list there that there are 2 suspended normal jobs, one of which is the one that hadn't had a chance to go yet, and the other one is the one that was running and then was suspended to make room for the important job. Okay. All right, so now I think it's finally time for Bob to come into work. So Alice has been using all of the GPUs in the cluster, including 8 that are reserved for the red team. But now the red team is here, and Bob submitted 16 GPUs worth of work, and he'd like to go. And since the quota belongs to him, one of Alice's jobs that's running, using the borrow quota, has been suspended, and Bob is now running. So with the borrowing and quota prevention system is flexible enough to allow the teams to get the quota that they're assigned to, but when they're not using it, other teams can use it. All right? So that's the end of that demo. And I think now we're going to switch to all right, so now I'm going to hand over to Claudia to talk about fault detection and observability.
And hopefully you'll know how to use this. All right, so we're going to switch a little bit context now, still in the same area of how do we run workloads efficiently and effectively on the cluster. But we want now to focus a little bit more on the reasons why we really care about fault tolerance and advanced fault tolerance in this case. So ideally, in the perfect world, we don't need any human intervention whatsoever in a cluster. So people just go, Alice and Bob, submit all their job, the cluster is always fine, no GPU breaks, everything is fine. That's, of course, not how things work. And therefore, to have the cluster to being used as much as possible and reduce the human intervention as much as possible, we need to focus on 2 things. One is the infrastructure itself. The other part is making sure that the workloads are running. For the workloads part, we're seeing all this the queue management, fair sharing, so all the good stuff that Dave and Olivier showed so far. On the other hand, we have the hardware. So we need to make sure that the GPUs are running correctly. And if they're not, we want to know that. So even to make sure that all the jobs can run correctly, and also one of the reasons why we need to adjust quotas is because maybe at some point a couple GPUs don't work anymore. So we need also to adjust the quotas accordingly, depending on the cluster state. And this is not something that's new and unexpected. I took some screenshots here from some of the most recent reports on GPU failures and how they relate to AI jobs running on more or less large clusters. On the top left side, I think that's probably the most famous one when AI Meta released the white paper about the training of the Llama 3 herd of models. They showed that very nice tables showing how many errors have been happening during the entire training period. And they can be software or hardware issues. In particular, the hardware ones, they account for 78, I think, yes, % of the interruption of the workloads. All those are only hardware. And of these 78%, almost 60% is GPU failures. So you really, really need to make sure that you can notice when things happen and hopefully also auto-recover the jobs. On the right hand, this is maybe like 3 weeks old, 2 weeks old, technical blog post from NVIDIA showing the error rates, both hardware and software, over a 4 or 5 months period where they've been running training jobs on their clusters. And again, a lot of hardware errors. On the bottom right and center, I reported also a screenshot from a paper that was just published 1 or 2 weeks ago by IBM Research and University of Illinois Urbana-Champaign, where that table there is showing how many jobs have been failing because of GPU errors during a time span of 2.5 years. And those jobs were more than 4,000. So long story short, need to take a look at those GPUs. And not only GPUs, also network, that's another big point of failure. Storage can be also a point of failure because you deploy an operator that's taking care of the storage nodes. So that's also subject to failure. So in our system, we rely on 2 components. Native tooling, everyone knows Prometheus, Grafana. For Prometheus, is going to provide node statistics about hardware, CPU, memory, network, but also information about the pods or the workloads that are running, how they're doing, and all of that. Grafana, great tool for visualization. And on the GPU side, with the GPU operator, they also provide the DCGM exporter, which is creating a lot of metrics that report the status of the GPUs. So all of that is a great, great starting point. Unfortunately, it's not enough. And we've been working to provide also an extended set of what we call health checks on the GPUs, network, and storage. That's been packaged into this tool called Autopilot, and that's integrated. So the results of Autopilot health checks are used by the app wrapper to figure out which nodes are good or not. Let's get into some details now. So why we have this Autopilot thing, why we needed to do this. So during the operations and bring up and running all the jobs on the Vela cluster that Olivier showed at the beginning, we've been seeing errors happening, or like a training job that would crash entirely, or that the performance would degrade, like the token per second and all the metrics showing how good the training is going, that would degrade. But if you look at the metrics that are exported regularly by the native operators, you would see that everything is fine. Until there is a real crash, a hardware crash, you don't really see some of the aspects that are degrading the performance of training job. And not only training jobs, also, of course, fine-tuning and inference are also impacted. So we've been seeing where those errors are, what to look into the GPUs to see why a job is underperforming. And there is nothing new that we are inventing, really. It's just a bunch of NVIDIA SMI commands or DCGMI commands. But those things that we're looking at are not exposed by the DCGM exporter, for instance. So we know what we're looking for. So the ideal, the thing we want to do is package all those things into periodic health checks on GPU, network, and storage. We run those tests all the time, and we can leverage Prometheus to export export the results that we're getting. And also we label the worker nodes, healthy, unhealthy, how unhealthy are they, and those labels are used to steer the life cycle of the jobs. So this is pretty much the tool, like a summary slide. So we use this to run automatically health checks on the cluster. We export data, Prometheus and labeling nodes, and we use this information to have the jobs running effectively. This is a list of the health checks that we're running. GPU, mainly related to GPU, also network, some benchmarking too. I'm not going to get into the details of that. Okay, so now we're going to see a short demo. We're going to install Autopilot and the entire observability stack by Kubernetes stack and the Grafana dashboards, and we see how those work. All right, so let's see if I manage to do this. Okay. Okay, great. All right, so here we're installing Autopilot. This is a Helm chart, so it's pretty straightforward to install. And I'm looking from here because I don't see it down there. Okay, so it's a Helm chart. We install it, and it will run on the GPU nodes. It can also run on non-GPU nodes, but in this case, that's all we have. So we're running on with the GPU setup. So since we are also creating an NFS client at this point, we can also extend the Autopilot configuration and check periodically that also the PVC creation and deletion is still working. So taking also a look at the NFS client. And we can just edit the configuration file, actually create one that we will gonna pass to the Helm chart. This is a plus that is not necessary, but since we have a storage class there that we manage, we want always to take a look at that. So we just upgrade the Helm chart, take a look that everything is fine. So this is going to run a rolling upgrade, so it's going to take a little bit of time. So I think I have sped up a little bit. Okay, so from the logs, you can see briefly what is going on. It has run all the health checks. Everything is fine. So it's labeling the node with a pass, saying that the GPUs are OK. The node overall is OK. Now we can move on to the monitoring setup. So we're starting with Prometheus. Prometheus and Grafana, they actually come together in the Prometheus community, the Kubernetes stack Helm chart. That's all on the Git repository that you can all find super easily. Links are there. So we just install the Helm repository, the Helm chart. We run an update. And so this chart will provide Prometheus, Grafana, Alert Manager, the node exporter, and Kube state metrics. That's all that we need to monitor the cluster. So it's all there. It's super easy to install. So in our case, since we're running on OpenShift, we need to change a few things. So we need to override the node exporter port because that's already in use. And also we need to not deploy the CRDs, but that's something that you may not need to do. So if you're running on an OpenShift cluster, just remember that that's something that you're going to need. So we can just create a configuration file for Helm chart. That's the usual way of doing things, as you all know already. And we just deploy the Helm chart. And it will take a little bit, but we're speeding up the process. So depending on where you're deploying, if OpenShift or Kubernetes, you will need to, especially in this case with OpenShift, you will need to add the service accounts that are created by the Helm chart to the privileged service account. So not service account, so the security context, and that will be needed so that all the pods are able to scrape all the information from the nodes. So we have all of that running, and the chart will also tell you how to get the to expose the service, the Grafana service, to access the web console, and we also give you the default, the way to retrieve that default password, which can be changed in the Helm chart, but we're not doing that in this case. So in this case, we're just exposing with port forward command, we're exposing the Grafana dashboard to localhost. So we're going to access it, and default user is admin, and the password is prom operator. All right, and at this point, so this is going to be empty, so you're not really seeing anything here other than the default dashboards that are in Grafana, just to showcase the capabilities. But we can import Grafana dashboards with that. The one that we have created for Autopilot, that is going to show all the health checks that is running, what is wrong with the cluster, if anything is wrong. And we're also going to deploy the DCGM dashboard from NVIDIA. And that's a pretty extensive dashboard that contains a lot of information about the GPUs. So we just, that's super easy to do. Both dashboards are, of course, on the Grafana website. And you can just copy the ID. That's all in the demo, of course, on our Git repository. And you can just copy paste the ID from the website. And yes, that's the NVIDIA one. Of course, you need to select the source of the information. Might be multiple, but of course, the default is Prometheus. So depending on which cluster you are in, if it's Kubernetes or OpenShift, you would need to let Prometheus know from where to scrape the data. In the Kubernetes case, you will need to label the service monitor, which is an object that you attach to a secondary source of metrics. In our case, it's going to be Autopilot and the DCGM exporter. In OpenShift, you would need to label the namespace where those metrics are being produced with the OpenShift monitoring label. So it will take, for the GPU will take a little bit to start scraping the metrics. And then, yeah, it showed up that everything was configured fine. And I think, OK, I didn't destroy it. OK, who's next?
Yeah, I'm next.
OK.
OK, great. So now we've seen how how Autopilot can detect the faults for us and how it labels the nodes for us. We're going to look at how the next levels up of the software stack use that information to automate fault recovery. So we're going to get back to app wrappers first. So I said, app wrappers are our mechanism for hardening workloads. In ML Batch, we really push users to wrap pretty much all their workloads inside of app wrappers. And there are a lot of reasons why a workload might be unhealthy. Pods can fail. And they stay failed for a while, longer than a grace period, so the underlying controller didn't restart them, didn't recover them. Not enough running or completed pods. So for some reason, pods didn't start, they aren't running, they didn't finish, again with grace periods. Autopilot could have labeled a node as evict, meaning there's a severe fault in that node, and then the app wrapper controller is looking and it sees there's a pod running on a node that's been labeled evict, and that pod is using a resource, in particular GPU, that's unhealthy. That's an unhealthy workload. We need to do something about it. Similarly, the top-level kinds, like a PyTorch job, RAID job, things like that, the batch job, they have statuses. And so if one of those goes to a failed status, then that means the workload has failed, and we can recover that. And finally, the user may go in and delete their top-level resource. They may kind of forget there's an app wrapper there and just delete the PyTorch job or delete some secret that was created as part of the job. And we interpret that as the user saying, there's something wrong with this workload. Please get rid of it for me. Or I forgot about it, but I need to get rid of it. And so diving a little bit more into the picture there, the app wrapper lifecycle sort of has 3 stages when something is admitted. So the job's admitted, and it gets to a resuming state. This is when we're creating the resources. So we're going off, we're creating all the resources, we're waiting for them to get to a start running state. running, which is the sort of normal state. And then if we had to do a retry, we kick into this retry state. And in that retry state, what happens is, resetting state. And that's where the app wrapper controller will go in and sort of first gently ask the top level resources to please delete themselves, and then sort of monitor, make sure that it actually happens. And after a while, go in and forcibly delete them without giving them a choice, to make sure that everything is fully cleaned up before it goes back into the resuming phase and tries again. And so this uniform retry loop has a bunch of parameters around grace periods and pauses and how many times you ought to go around it. And the system is set up so that the cluster admin can sort of set reasonable defaults for these, and then users can override them with annotations within bounds. So the cluster admin can also say, you can retry, you can do certain things, but you can't make this pause longer than this long, because that's against my policy. I want to make sure I get good utilization out of the cluster. So that's the sort of app wrapper piece of it. Another thing we do is we adapt to available resources. So this picture on the bottom here is showing a cluster where there are actually 3 teams plus a Slack cluster queue. The green nodes represent nodes. So the squares on top represent nodes. So the green ones are healthy ones, the red ones are unhealthy ones. And so we have a mechanism where we reserve this Slack cluster queue. And so what we do is we have a reconciler that's watching the status of nodes. It notices when Autopilot labels a node as unhealthy. And when that happens, it adjusts what Kueue calls the lending limit on the Slack cluster queue, so that the available quota to be borrowed by other teams in the cohort actually matches the capacity in the cluster. So at all times, we're sort of dynamically adjusting this Slack capacity so that what we have available to hand out to the jobs actually matches what's healthy. This gives us the ability both to have the thing this gives the ability to prevent admitting too many new jobs in the future. And we combine this with node anti-affinity. So as jobs get admitted to the cluster, they get steered away from nodes that have been labeled as unhealthy by Autopilot. It also gives us the ability to reserve the quota to migrate jobs away from the unhealthy nodes. So if we're reducing the quota we're handing out, that gives us the room to then reset the app wrappers and reset those things and have them go back to healthy nodes when they come in. And it also allows us to sort of view maintenance as just another unhealthy node. So if admins need to come in and start doing things, they can cordon the nodes, and the system reacts to that just the same way it does as if as if Autopilot had labeled something as unhealthy. It goes ahead and adjusts the quota and sort of starts steering new workloads away from those nodes that have been marked as unhealthy. So sort of summing this all up, we have Autopilot at the bottom, sort of periodically checking things, labeling the health of nodes, GPUs based on networks, GPUs and storage, labeling nodes to let the rest of the system react to that. We have the app wrapper, which is sort of watching the workloads. It's injecting the affinities automatically, so the users don't have to get that hunk of affinity YAML correct. It gets it put into all of their workloads for them to steer their pods away from unhealthy nodes. It detects when pods are running on evict nodes and triggers a reset. And it automates this whole control and reset and resume cycle on failures. And it also does this capacity management to inform Kueue of the unhealthy nodes. So now we're going to show a demo of this. Show a demo of this happening over here. All right. And so in this demo, what we're going to do is we're going to have Alice submit one single large job. Our cluster isn't very big, so it's a 3-node cluster with 24 GPUs. So Alice is going to submit a job that takes 16 GPUs. All right, so here she goes. She's going to submit this, and we can see that the job is running. And then what we're going to do is we're going to go ahead and pick one of these nodes as a victim, and we're going to label it as if Autopilot had detected a severe GPU fault on it. And we're going to see the system then react to that. So we're going to pick this victim node, go ahead and stick in the Autopilot evict label on it, and then we'll wait for the system to react. This will take about 30 to 45 seconds. And so what we're going to do is we're going to go ahead and watch the app wrappers. So there's the single app wrapper for her job. It's running. And what's happening now in the background is the system has a node monitor. It's noticed that this node has been labeled. It's then looking to see, are there pods that are running on a node, this node in particular that's bad, that are actually using resources. So is there a pod running on this node that's using a GPU, in which case we ought to reset it. And so once it does that, it'll then go off and from the pods, go back to the app wrappers, figure out which app wrappers need to be reset to do this, and we'll put them into a resetting state. And then here he goes. All right, so now it's reset it, and the resources are being deleted, the pods are being deleted, being cleaned up, and they're gone. And so now we can resume. and the workload is now running again. And if we look to see where it is, the anti-affinity shown there on the right or left, whichever side they are, have steered the new pods away from getting onto that bad node. And so now they're running on the 2 remaining healthy nodes of the cluster. And that's all happened without any human help. All right, this all just happened with the system taking care of everything. Okay, so that's the demo of that. And get the mouse over here. Okay, so what we want to do now for the last section of the tutorial is we're going to take you through 3 sort of representative workloads that we run in this cluster. And all of the YAML and definitions of these are available as part of the tutorial. But we're just going to talk about each of them quickly and show them running. So the first one of these is the Kubeflow trainer. So the Kubeflow trainer is an operator for it's Kubernetes native framework for fine-tuning, scalable, distributed training of LLMs. It supports a bunch of machine learning frameworks. And for our demo, what we're going to do is we're going to take a PyTorch job and do FSDP, so fully sharded distributed parallel training of a small job. We're going to put that inside of an app wrapper for enhanced fault tolerance. And we're going to go ahead and do that. And so we're going to look at the demo. Okay. So again, so this stuff is out here. So what we're going to do is, first we're going to go ahead and do the kubectl apply for this job. All right, so we're going to grab the command, go ahead and apply this YAML. And so this is create an app wrapper that wraps around a PyTorch job that's going to go into this training job for us. And we can see that it's starting to go. It's created, it's running. So we use here's the YAML. It's way too big for you to read. But we created this YAML actually using a Kubeflow trainer notebook. So we used a Python notebook to take some fairly standard training code for Python code for doing this. And then we used the training client to actually go off and create that YAML for us, which we then grabbed and used a tool from MLBatch to take that YAML and inject it inside of an app wrapper for you. And so all this stuff is available. And the job is actually finished now. And if we go and look at its logs, we can sort of see what it did. So it ran this training job. There's some snippets down there at the bottom. You can see that it ran, it ran with 2 GPUs inside of each of the 2 pods. And then here's the output from the actual training. And when we're all done, we can go ahead and delete things and clean up after ourselves. Okay, so that. Okay, and I think I'm handing it off to Claudia next, I think, right? Where are we? Yep.
Okay, so now we're going to see an example of fine-tuning, and for that we're going to use Kueue. Kueue is the Kubernetes version of Apache Ray. Ray is a framework that goes end-to-end in entire ML lifecycle. So you go from data preprocessing up to model serving, and it gives you a runtime for distributed to run distributed workload, and also an API with a very nice Python module, and also a CLI to run, to submit jobs, and also create jobs through the Ray API. So that works out of Kubernetes, and in Kubernetes, Kueue is the one that will work in Kubernetes and the one that we're going to use. The install is super easy through a Helm chart, and among the nice feature is the Ray autoscaler that will help you scaling up and down the workloads in a very transparent way. The fine-tuning demo is an adaptation from a blog post from Red Hat, which in turn is an adaptation from a demo that you can find on the Ray Git repository. So we're going to do, again, fine-tuning with Ray, and we're going to train Llama 3.18 billion on a grade school math dataset. With LoRa enablement. So the demo is going to be set up the environment. We're going to run the fine-tuning job through the Ray API and within an app wrapper. And so we're going to submit the job, and we're going to follow how that goes on the array dashboard. So, okay. All right. So we need to install some prerequisite. It's just to set up the Python environment. So it's a one-liner where we're going to install. The major is going to be the array CLI from which we're going to submit the job. So it's a super easy and quick setup. To run the job, we also need some storage because we need to first, of course, download the Llama model. And that's also where we're going to save the checkpoints, where the fine-tuned model is going to be. So we are creating a PVC. And for this entire demo, we're going to impersonate Alice. So we're going to run in the blue namespace, and with the --s Alice, we're saying that we are Alice in this case. So we created the PVC. At this point, we're going to create the array job. So here we are using an image from Kueue produced by Red Hat with the array runtime. Of course, you can use the regular array images provided in the Docker Hub. So we're going to run on one GPU node. So we're going to use 8 GPUs. And we're going to set one GPU for the array head, which is like the master, and 7 for the array worker. So we're going to have a total of 8 pods. So we're going to wrap this in an app wrapper, and then there is a very nice utility in the ML batch repository that, given any API object, will wrap that into an app wrapper. And we're going to use the default queue, which is the one that Alice can use. So we create the app wrapper. We just take a look, and we see that in the default queue is the one that's going to be used. And the array cluster is exactly the one that we have specified in the YAML file. There is no change there. So we're going to submit the job by applying the YAML file. So at this point, an app wrapper is being created, and since the node is empty, it can run immediately. So we can see that the array head and the array workers are being initialized. It will take a few minutes. OK, so at this point, we can use also the array dashboard to monitor the job, which is pretty handy. Instead of looking at the logs, you can just take a look at the dashboard. So we're port forwarding, so you can see that on localhost on the default port 8265. So at this point now we can set up the fine-tuning. So we're cloning the repository where we can find the code. That's of course open, and through the Python API. The array Python API, we are creating the job with the specification that we need. And we set up all other things like where to download the model. In this case, in the HF home, so the Hugging Face home is going to be on the PVC. So we have one copy for all the pods. We are saying that we're running on 8 devices in total, which is the number of the GPU nodes, in this case, 1 for the array head and 7 for 7 different workers. So we create this very short Python code, and we run it. And this is through this array API, it's pretty much packaging the entire thing. You can imagine it as like when you package things into a Docker container. So we'll create one package, and that package contains code and instruction, dependencies, everything that's needed for the job. And that code will be running on the array head and the array workers. So also the head, despite that's the one that's managing the job distribution, that's also doing some actual useful work. So we're waiting for the job to be submitted, and then we can follow the actual work either through the array API on the CLI, or through the array dashboard. So this is taking 15 minutes, so of course we're not staying here for 15 minutes. I sped up the process. But there are a few things that we can put some attention on. So in the dashboard, you're going to see on the bottom the logs of what is happening. And those logs are in the array head, so you can also monitor from the kubecli. There is also the array core overview where you can see all the tasks that are being executed. And through the cluster menu, you can also see what's going on in terms of resource utilization. So we see that the GPUs are working, good, because that's what we wanted to do. And yeah, through the array core overview, we can see which jobs are the total number of jobs, the ones that are currently running, how many are in the queue, and all of that. It showed up at some point, but since we're speeding up the process, we may have missed it. So when the job is succeeded, you can see that on top. And at this point, we're just going to take a look at where the data is. So we're executing a terminal in any array pod will work. We are in the array head in this case. And we're seeing that in the slash model, that's where the PVC is. And we have both this checkpoint is last one, that's where the checkpoint that we have been with the fine-tuned model that we just run. And I think that's it for me. And now
Thanks, Claudia. So we have just one last example workload to share with you today. Another really important thing on our cluster is to run models and inference. So here I'm just briefly going to show you an example batch inference. In this example, we're running vLLM. You've already seen vLLM mentioned in other talks. In this conference, this is an inference runtime, originally coming out of Berkeley, that is now part of the Linux Foundation, and one way to run machine learning models. And what we want to do here, so we're going to run an IBM Granite model in a pod, and what one wants to do is submit a batch of requests and collect some statistics about the behavior of the model. Right, so the way we do that is sketched on the right. We have an app wrapper that contains a job. This job itself has two containers. Again, one container runs the inference runtime, one container runs the load generator that creates the request, and the request collects the responses and so on. And I think, as we mentioned before, one of the things with models, they are big, so we don't want to have to load them every time we run such a job. We want to cache them. So in this case, we use a persistent volume setup at the bottom here, set up here in our pod, so that the first time we run the workload, we're going to download the model waste from Hugging Face, but the next time we run the same workload, we won't have to do this again. The details of the containers are here. Pretty straightforward. On the left-hand side, we're running vLLM, and on the right-hand side, we're running our load generator with a number of parameters. Here, we're just submitting, for simplicity, demo's sake, we're just submitting random requests, and we're measuring what happens with the model. The only non-trivial, somewhat ad hoc, somewhat ugly thing here is we need these two things to synchronize, because we want the server to be running before we start measurement, and when we're done with measurement, we want to kill the server, right? So different ways to do that. What we found in practice is that users are not really good at building their own container images. There are lots of reasons not to build container images. So here we use an upstream container image, unmodified, that we can trace and so on. And then we do whatever kind of synchronization we can manage between these two things. I could show you a demo, but it's probably, maybe I have a second to do that. So essentially, again, this is exactly the same as all of these demos. This is what you'll find in the supporting documentation from the tutorial, with the specification on the left of the workload. I mean, first I'm going to skip the persistent volume definition, but skipping on that, we just copy-paste the workload definition, the YAML you've seen in the previous slides, in my terminal here, and then I can run, I can capture the logs of the two containers in my pod. The first one is starting to load the model. The second one is waiting for the model to be loaded. Eventually, the model is loaded. the inference can start, the load generator can start sending requests, we're processing requests, and at some point in the end, oops, I went too fast. At some point in the end, we get the statistics out of this particular test run, and we can compare, let's say, with a previous checkpoint of the model, and say if we're doing better or worse. So let me try to wrap up here. No, I don't want to play this again. So what we realized when we started trying to have a Kubernetes cluster with GPUs to do AI is two fairly obvious things. The first one is our admin had no clue. They didn't know about GPUs, they didn't know about AI. So they needed a turnkey solution, something they would really could deploy in their cluster without having to think about pretty much anything, right? The only, and what we've tried to share with you today is that, the only thing you really have to think about is what are the quotas you want to give to the various teams, and that's essentially the only thing that then admin has to do to deploy this setup on the cluster. The second thing we've realized is that AI, ML experts, domain experts, they don't understand anything about Kubernetes, right? So what they need is pre-baked templates. If you want to pre-train a model, this is what you do. Maybe a number of ways to do this, but here's the collection. If you want to fine-tune a model, this is what you do. If you want to do data preprocessing, this is what you do. If you want to do inference, this is what we do, right? So what we've tried to share with you today is, again, some of these templates here, right? So unfortunately, we cannot really provision a GPU cluster for every member of the audience, so we went through this through video, which is not entirely ideal, but hopefully you'll get a sense. And again, the key idea here is that all of what we've shown you is just turnkey kind of solutions. So before we conclude, I want to just share what it means in practice, right? Here's one of our clusters we manage in IBM Research. It has about 1,200 GPUs. And this is a snapshot I took last week as I was preparing those slides. So at that point in time, we had about 20 teams onboarded on that cluster, right? And the quotas for those teams were essentially what you see on the left pie chart here, which is, you have two teams that more or less have access to a quarter, nominal access to a quarter of the cluster each, and then a bunch of other teams, right? And there's a bunch of extra capacity that is not nominally associated with any particular team. And what you see in the middle is what we end up with, right? With all these teams submitting a number of workloads to the cluster, we end up at the point I captured this particular snapshot of the state of the cluster, where 1,206 GPU utilized in the cluster, and just a very small fraction, less than 1%, I guess, of 10 GPUs not currently in use in the cluster, either because we are transitioning between workloads or because there wasn't any really small workloads that could still fit in the cluster, right? So if we were to compare that, for instance, to using Kubernetes quotas to do the same thing, which is to enforce strict quotas and saying, for instance, the blue-gray team cannot go above its quota, we would have lost essentially one third of our cluster would have been idled at this point in time, right? So what we're trying to say here is with this system, we've managed to do these two really antagonistic things, which is one, guarantees quota to teams. So for instance, if the green team at the bottom comes back and say, hey, I need my 16 or my 32 GPUs, they're going to get them. But at the same time, we're never really wasting any kind of GPU capacity that we have that is, again, really fundamentally unacceptable. So I've shown this before. Again, we try to went through all of these kind of key features that our stack need to have to really be functional, right? Other than what I just said, which is essentially be self-maintaining and no question asked when you deploy and you manage it. And again, a lot of that has to do with this community and taking advantage of all the great work that is happening in many different places, and finding the proper way to get these things together, jointly configure them so that they work together and give all the capabilities that we want. So thank you very much for attending. You can look at, again, you can find all the details of what we've shown you videos, everything at this QR code. If you're also interested, if you're in general interested in platform for AIs, right, on Kubernetes, we have a number of talks in the rest of this week with from IBM Research and friends like NVIDIA, like Red Hat, and others about different aspects, other aspects of this platform, sustainability, compliance, benchmarking actually, and data preprocessing also, which is one we have an entire talk about that. We didn't show any templates, workload for data processing, but the second talk will have a lot about that. Once again, thank you very much for attending.